So one of the reasons you might be here tonight is you might have some interest in this topic, okay? And I found myself after having talked with Bill, our speaker here, being pretty sensitized to the news and there's lots of stuff that every week I'm seeing stuff in the news here. This is an article that was in the Wall Street Journal. Investors pile into electricity gaps. Well, why? Well, actually, electricity is the busiest desk at HC Group, a London-based headhunting firm that focuses on commodities. Over the past year, the firm has helped financial firms with more hires in power than in oil. An executive company said, behind the boom are two trends: the rise of energy-intensive artificial intelligence and of electrification due to the energy transition. The International Energy Agency projects that AI's energy usage will rise tenfold over the next 2 years. Pretty interesting. Forbes, AI power consumption rapidly becoming mission critical. New York Times, just last week, AI's insatiable appetite for energy. A lot of paragraphs. One peer-reviewed study suggested AI would make up 0.5% of worldwide electricity use by 2027, or roughly what Argentina uses in a year. So the AI could use the equivalent of what a country uses in 1 year. Analysts at Wells Fargo suggested that U.S. electricity demand could jump 20% by 2030, driven in part by AI. Dick Parker also has articles about, whether we're equipped to actually handle an increase in electricity and whether our networks are able to do that. So a lot of stuff in the news here. So with that, I'm going to bring up Bill. The Bill's going to talk about systems and software for averting an energy crisis. He is the principal systems architect for Woolley Inc., designing advanced memory and storage solutions for data centers, artificial intelligence engines, and automotive designs. He's been active in memory-related scans activities, including chairing the GDEC Alternative Memories Committee, I think for quite a few years, if I recall correctly, and serving as a working chair of the NSF Center for Memory System Research, CMSIS.
How do you pronounce it? I pronounce it ChemSys.
ChemSys, sorry. He's a Board of Trustees member of Bridge to Connect, a STEM education outreach program. So with that, I'd like to bring up Bill. Who's welcome.
So I'm a hardware guy. That's the end of my talk. Oh, nobody left. Okay. I guess you're sticking around to see what else I have to say. That's good news. Let's bring up some information. There we go. Okay, so the topic I wanted to address over here is we have a potential energy crisis, and Daniel started to touch on this. The last 2 years I've been working with the United States Department of Energy on analyzing this particular problem. And I'll show you some data here, but it gets a little scary. So starting with me, I do a bunch of stuff. You guys can read through that, but the thing I wanted to really start with was over dinner tonight with the executive team, I was reminded of a point in my career where I started out as a test engineer at Intel, working on 1 kilobit DRAMs and EEPROMs and boards using them, 8080 microprocessors. And then I transitioned from test engineering into diagnostic engineering. Now, if you know the role of diagnostic engineering, that's the software member of the hardware design team. And I was on a project team of 30 people. 2 diagnostic engineers, 14 hardware engineers, and 14 software engineers. We had a pizza party to celebrate the shipping of one of our products. And so the other diagnostic engineer and I were sitting across from each other in the middle of the table. To my left were all 14 software guys. To my right, all 14 hardware guys. In front of the 14 software engineers were 7 pitchers of Diet Coke. In front of the 14 hardware engineers were 14 pitchers of beer. And I thought, is it really that obvious a difference between nerds and geeks? But let's move on and talk about the subject matter. And so what I wanted to start with was this United States Department of Energy. The program is called EES2, Energy Efficiency Scaling with a doubling for the next 20 years. And so a number of companies are signed up there. You can see a selection of the companies that participated there. I participated actually with 3 different groups, so I ended up writing a number of different parts of the proposal that comes out of this, which is a 335-page report that is going to the US Congress and to the White House as part of the CHIPS Act funding distribution. Going to show you why. Here's the current trajectory of power consumption. That top line is the line of the capability of the planet Earth to produce energy. And that includes assumptions like that we bring nuclear power plants back online. But you plot out where electronic devices such as the internet are going, and you can see that that trajectory is problematic. In fact, the DOE projects that by the year 2055, those lines cross, and all of this innovation that we're working on now halts. We got to do something about this. So where is all that power going? And that power is going a number of places. This breaks out things like data centers. And you can see that data centers are going through this phenomenal increase in demand. You can see that consumer devices are a bigger portion than data centers back at the beginning of this study, but they start diminishing as a percentage of the overall consumption. Networks are exploding. The introduction of 5G and multi-gigabit Ethernets, all these other things are driving this power budget very much out of control. So then we broke down where are we spending it in the architecture of our systems. And so there will be a test on this, so make sure you memorize every number in this table here. But essentially what it's saying is that what we need to do is we need to look at the energy efficiency of our hardware and figure out how we're going to solve this energy crisis. Well, as part of that analysis and why I'm here, software is obviously a big part of that. You see all this stuff down here, this kind of flat area here? This is all your standard processing. This is your databases. This is your HTTPs. This is your standard processing. And this is a logarithmic scale. The far right is cryptocurrency and artificial intelligence. 1 million times less efficient than standard programming. Python programming is potentially part of the problem in that we have Python programming that is partly interpreted and it has a lot of the inefficiencies of doing matrix mathematics, and ChatGPT and a lot of these other programs that are emerging are based on Python. Cryptocurrency is already over 0.5%. In fact, the latest numbers I saw is that cryptocurrency is now closing in on 1% of worldwide power consumption. It's absolutely crazy. By the way, this is not a good thing. So here's the matrix that we broke down in the report. And what this plots out is the number of years to technology readiness level 6. In other words, mass production ready technologies. So anywhere from 0 to 10 years out, 15 years out, it's a 20-year program. So they want to look as far forward as they can to imagine where we're going to get these energy gains. On this scale, are how big an impact would certain changes have on this energy problem? So because this is a software audience, I thought I would zero in on the things that apply most to this audience here. So I broke down like that cluster where we have anywhere from 100 to 250 or 300x potential improvements come from things like reducing the energy for machine learning, algorithmic specific energy, that we can actually build architectures that are energy efficient that accomplish these tasks. And then software for these emerging architectures. Yeah, Python programming is great, but where do we have that highly efficient Python compiler that goes down to machine level code that would have the efficiency of a C++? We don't have that today. And that is desperately needed to get these 100x to 300x improvements in efficiency. Then dropping down one additional layer, you see things like algorithmic specific energy, languages, compilers, and so forth. There are lots of other things here, and these are still pretty darn good, right? These are in the 20 to 50x improvements that are possible in the architectures from these methods. So, like my career spanned a lot of different things. My career went from test engineering to diagnostic engineering to writing CAD tools. I've written some hundreds of thousands of lines of code myself as well. But then I switched over to the dark side and got into hardware design. And so, preface this with some of my data may be a little bit dated. And that's what we're here to have an open conversation with. At the end, I really want to open this up to hearing from you guys, what can we do better? Because this is not going to be my last talk on this subject. And I want to learn from you as much as I want to show you what I've learned and make this an interactive process. So what can we do together to save the planet? I'm sure you guys are painfully familiar with the fundamentals of computing. And if you simplify it, it breaks down to processing, memory, storage, and communications. And then we put these structures around them in operating systems and application drivers and so forth to make these resources available to the application programs. So in this context, over the years, we've developed this really pretty picture of a pyramid. Who else has seen this picture before? Yeah, pretty much everybody has seen this picture that represents the relative number of memory cells or cells, and then the cost and the latency and so forth. It's a really, really pretty picture, but it's also extremely misleading when you want to do power analysis, because it completely ignores the fact that all of these are on different buses. The registers are inside the chip, and they have caches, and they have RAM over on one port, and disks are on another port, and they have communication channels on a third port. These all apply when you want to do a power analysis, because you can't just make nice smooth transitions from one tier to another in that pretty pyramid without going through these buses. So that's what I wanted to zoom in on. It's like we take just a classic example. What if we want to run an application? We're going to take that application from the disk, load it through the CPU over one bus, transmit it on another bus to deposit it into the RAM. Then we're going to read it back from the RAM into the processor so that the registers and the execution units in the processor can execute that. Then we're going to run some communications data from the CPU back over to the RAM, so that we can then consume that data back to the CPU over that same bus, and then store the results out to disk. All of these steps burn power. And so the fundamental message that I'm going to leave you with tonight is we need to do better at doing work and not just moving crap around. So take a look at some of the sources of inefficiency. One of the sources of inefficiency is just the registers themselves. I come from an era where my first computer that I programmed was 16 kilobytes. And you had to count your bytes. You had to pay attention to things like whether it was an 8-bit or 16-bit variable that you were defining, because you had to pack your program into that small address space. So there's an inherent inefficiency there. The next inefficiency comes from caches. Over the last 40 years or so, we've all had caches on the CPUs where the standard cache line these days is a 64-byte cache line. So now let's take a look at what this means in terms of an efficiency. Well, you have first the discrepancy between the integer and floating point sizes and that cache line. But then my friend Joe is one of the vice presidents at AMD. He just goes on a rant about how his company builds these artificial intelligence engines, and they gobble up gigabytes of data, but the end result is he wants to know, is this a picture of a dog or not? That's one bit of data that could tell you that. So the efficiency level of that one bit is a wasted 99.8% if all you wanted was one bit out of this. So I'm not saying that our system architectures are completely broken. There are reasons why they are the way they are, but it doesn't mean there aren't changes we can make to improve on them. The first one is hit rates. The reason that caches are really not the evil that they sound like with a 0.2% efficiency is that the hit rates are actually very high. In excess of 95% for the most part on the various levels of caches on the CPU. So the likelihood that you're accessing multiple bytes or words or D words out of that cache is pretty high. Therefore, you're not wasting that much energy by doing cache fills and cache flushes. However, let's take a step out from the cache. When we get out to DRAM, now this is DRAM attached directly to the CPU. Our efficiency has dropped from 95% to 82% on reads and 62% on writes. So we still are getting an advantage by buffering some of those operations, but our advantage is diminishing very rapidly. Now, as these data centers have gotten huge, multiple tiers of memory are being created. And we're going to go into some details about this hardware situation. But essentially what's happening is that our hit rates are down below 65%. And if they drop below 50%, why are you bothering to cache anything at all? Because your accesses are simply overhead at that point. So here's a question, because I'm one of the chairmen of the JEDEC Standards Organization, and I help define things like DDR memory and flash devices and so forth. One of the things I asked the CPU guys is, why are we doing open page cached operations on memory? And they said, well, because we do speculative operations. We do speculative reads on those caches so that in case we need the data, it's there. And we get a quicker access time to it. So I said to a guy from Intel, so how many watts are we expending, and what is the percentage of performance improvement that comes from that operation? And he didn't know the answer to that because no one has paid attention to that before. Everybody has focused on bandwidth and performance, and the question of energy efficiency has not been significant to even the top tier companies like the Intels, AMDs, and IBMs, and so forth, until recently. In the JEDEC Standards Group, for the first time in the 30 years that I've been a chairman, the DDR6 survey said, power is more important than performance. So this is a coming trend. Next level of inefficiency. Let's look at disk drives. Okay, so we have a 4 kilobyte block that we read out of a disk. We pop it over 64 byte cache lines at a time. And that's great, except what if you profile how much data is actually being used by these applications? So my company did an analysis of some databases and fsync and a number of other applications. And the answer came out nearly identical for every one of those applications, that on average, 100 bytes out of that 4 kilobytes are being used. That means we're down to a waste of 97.5% of the energy. All we're doing is moving data and not using it. And this is the best case. This is assuming that your DRAM is directly attached to the SSD. What if that SSD also has a cache? Then it's doing 2 write operations. So now your efficiency would be half of that 2.5%. Now you're down to 1.25% efficiency. What if it's also being loaded into other side memories? You see that efficiency keeps going down, 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 down. What if it's over 2 hops over a fabric? Then you're doing a transfer, a transfer, a transfer, then the write. It's not a good formula. What about DRAM itself? This is my specialty. I've been spending the last 30 years of my career defining memories. DRAMs have a 1 kilobyte page size internal to the chip. So every time you activate one chip, you get a kilobyte read out of the sense amplifiers, and read out of the core to the sense amplifiers, and that is a destructive operation. It destroys the data that was in those capacitors. Therefore, it needs to be written back out. Now, there's not just one DRAM on a memory module. I mean, you've all bought them and put them into your systems. There's 10 across. That means 20 kilobytes of data are moved every time you want to do a single access to a DRAM memory module. And if that's a 64 byte cache line you're trying to fill, now you're down to 0.025% efficiency. This is not good math. So computer systems have been evolving, our entire lives. And what I've shown here is the projection for how we've increased the frequency of the memory, getting better performance, and how we've increased the capacity per memory chip. 16 megabit up through 16 gigabit, and the 32 gigabit is just about to come out. So that's the good news, is that we've continued this evolution, but it's slowed down a lot. As you can see, that we went from 6 years between quadrupling frequency to 15 years to quadruple the frequency. In memory capacity, we went from 3 years to 7 years to quadruple the memory capacity. It's slowing down. And at the same time, we've been losing the number of memory slots that you can put on a channel. With DDR5, we're about to make the transition to 1 slot per channel. So with the memory capacity slowing down, we're about to lose half of our memory capacity in the data centers. This is the crisis that the industry is facing right now. And this made a lot of people very, very upset. So let's take a look at where we're going to go with this. Where's this demand coming from? At the same time that we're slowing down the ability to add more memory, we have things like artificial intelligence algorithms that are suddenly becoming extremely popular. And just in the last 3 years, we've seen the databases for machine learning, the LLMs, the large language models, have jumped from 80 gigabytes to 240 gigabytes, and next year they're projecting 1.8 terabytes for an LLM. And at the same time, we're slowing down how we can give them memory. So we have a problem there. So we're trying to tackle this problem and give memory in lots of ways. The first one is something called high bandwidth memory, or HBM. This is a very popular memory solution that is attaching directly to the GPUs that are implementing the AI algorithms. Now, with this, it's a great solution, but it's very limited in the capacity, and it's extremely expensive. This is like, we're talking about at least 10 times the cost of any other memory solution out there. So, what about stealing your neighbor's memory? I'm sure all of you have worked with non-uniform memory architectures. Those have been in the industry for some 25 years or more. And so the idea is if you run out of memory on your processor, you go over a fabric to another processor and steal his memory. Well, that's great, except that until recently, these were all proprietary. Intel had QPI moving to UPI. AMD had hypertransport going to infinity. They were all proprietary. So finally, a couple of years ago, actually in 2019, fortunately, things all changed. CXL, Compute Express Link, was something that Intel had developed as a proprietary technology, and they gave it to the industry for free. They turned over all their IP to an independent organization. And in 48 hours, the rest of the industry followed suit. So CXL is now the established new fabric for expanding systems. And this is great in that it now allows for a whole new way of imagining, virtualizing the hardware in the system. And all of those resources, memory, storage, communications, and so forth. So with this consistent address space, now you can do a mix and match. And this is really exciting. And for me personally, and the work that I do with Wally, this is specifically what we're going to be targeting. And I'll show you a quick example of what we're looking at. But this, again, focus on you. So what comes out of this NUMA picture is that we've always had this situation where you knew you could get to your caches quickly. When you went out to DRAM, a little bit longer latency, but we all lived with that. Then NUMA. We went out to the neighbor's CPU and grabbed some of that memory, or we went to NUMA hops. And what you're seeing here at the bottom is that the latency continues to creep out. So that's obviously one of the things that software people need to be aware of, is that NUMA is not only not going away, NUMA is going to get a whole lot worse. And so we as an industry need to address the need to make NUMA work for us instead of against us. Because now CXL has been thrown into the mix. And you can do direct attached, you can do through one switch, you can do through two switches, and you can see that your latency increments keep going out, out, out. You might have 80 clocks of access to the cache, but you might be 300 clocks of access time out to a 2-hop CXL memory solution. There's also a new thing that's emerging into the marketplace, and that's a virtualized resource. And I give Samsung credit for being kind of the first to introduce this concept with something they call memory semantic SSD. And the way a memory semantic SSD works is that it advertises itself to the host CPU as a DRAM that is the size of NAND. And then as you access those pieces of it, it maps various portions of the NAND into the available real DRAM space. And so as one DRAM resource gets depleted, you can do standard cache operations of retiring that cache line, of marking it, and so forth. So this introduces yet another tier to the picture. So this is great in that CXL introduces a standardized way for companies to invest in offering solutions for this space. You may have heard that it's gotten extremely expensive to make an ASIC these days. So people want to be able to amortize that cost. This is what's going to help us do that. Now you can do memory pooling, you can do memory sharing, and in particular for AI, we now have a situation where you might have the database for your inference engine share in one of the resources and then have multiple CPUs sharing that database for doing your inferencing. So that pretty triangle that we showed, we can make that a lot uglier. I already showed you what the electrical connections are, but now here's what your latency map has grown out to be. And this is just the reality that software people are going to need to comprehend all of these latency issues and figure out ways to make sure that the system performance is optimized based on where you are in the tiers. AI in particular is extremely memory sensitive. The roofline model represents this idea that you can keep getting increased performance of your AI engine until you hit your memory capacity. And that flattens out. You can no longer do your inferences any faster once you hit that memory limit. So this addition of new memories is raising the roofline. And this is where your improved system performance is going to be coming from. But this does mean that you're going to have different latencies, different performance characteristics of those memory tiers. So knowing what data to put where is going to be a critical part of the solution. Okay, that's the hardware part of the lecture. Now, let's switch over to what you guys might care a little bit more about, which is what can we do? Well, I wanted to start with a personal story. Back in the 1980s, I worked on the boot code for a voicemail system for a company called Octel. And I initially wrote the memory test in PLM, which is a C-like programming language. It took 27 minutes to boot the system. And no customer was going to be satisfied with a 27-minute boot time. So I did fortunately, the PLM compiler was able to dump out the equivalent assembly code. I went in and hand-tuned the assembly code and got that execution time down to 7 minutes. Still not good enough. Nobody's going to wait 7 minutes to boot their voicemail system. So then I used clock counts and loop unrolling and every trick that I could pull out of my quiver and got the execution time down to 7 seconds. This is a 231x improvement in performance. And it taught me a lesson that high-level languages are great in that they let you develop code quickly, but that not in every situation that you can stop there. And that's kind of the bottom line message here is that this is a good lesson for things like Python. If you're going to do these matrix operations, there needs to be some way that this industry develops to optimize that so that we're not spending all of our time and all of our energy on execution time differences like this. And that low-hanging fruit is out there. So I've always thought that, we do what we know, right? We know a particular programming language. I know PLM, I know C. I might write everything, well, and I know assembly. I might write everything in those 3 languages because that's what I know, and I know I can get the job done quickly. But that doesn't mean that you should really stop there. Sometimes you really need to look beyond what you know and maybe learn something new in order to get around these problems. And so, yeah, I pulled this little statistic out about the relative performance of these languages. And you can see the scale from C to Python and a number of other languages in between. This is basically a call for give us better compilers, keep your learning going, learn as many of these as you can reasonably get away with, and so that you have multiple tools at your disposal when you're faced with a problem. You might be a great Python programmer, and if your boss wants you to write a calendar program, Python's probably not the most efficient language to write it in. So let's talk about some specifics. One of them is don't be lazy. You know, I had to figure out whether to do 8-bit versus 16-bit integers in the 1970s and 80s. Maybe we need to start rethinking that and making sure that when we're declaring variables, that we're using the appropriate size variable for the job that we're trying to execute. If we know that a loop is not going to run more than 255 times, why do we need a 64-bit floating point for the loop counter, right? That sort of thing. Next one I want to jump into is closer to my personal experience, and that is the various APIs. All of these resources are out there on the system fabric, but there are lots of ways to get to them. And choosing the most appropriate way is yet another way to get better efficiency. For example, we know that NVMe is a common way to access a disk. But as I've shown you, NVMe, on average, is only about 3% efficient. What about if we were to have a direct access to the memory? By eliminating that block level access, we can now increase the efficiency by leaving the memory remote and only pulling out the pieces that we use. And this is a hardware change. NVMe executes over the I/O bus, PCIe, or what's now known as CXL.io. CXL bus directly accessing memory is a much more efficient mechanism where we can get a lot better performance. Another one is DAX. Who's familiar with DAX? Direct memory access. It's a library that was developed by Intel and Microsoft. It's now available in Linux as well. And DAX is an important transition if you're writing a new program, in that it, instead of using standard file I/O where you take an OS trap every time you do a read or a write call, DAX opens up a memory mapped file. And now you can use memory commands so your task doesn't have to get put on the reserved list. Your task can stay active, access the data without trapping out to the OS. The improvements in performance and in efficiency can be more than 1,000x by going from a file model to a memory mapped file option. And it's still the same read and write commands, but it's to a file, in a memory map file instead. Let's see, another one is pooling and sharing. I talked a little bit about that we can now start using memory resources more efficiently by letting multiple processors access them. And so you can reduce the amount of traffic that way. And finally, there's persistent memory. Persistent memory is memory that does not lose its content on power fail. So like battery-backed RAM is one way of implementing persistence. The baby specification is a software bit that manages the ability to detect that power is about to fail, signal the hardware to go do a backup from DRAM to flash before the power goes away. And then when power comes back, it restores the contents of the DRAM, and you can keep going as though nothing had happened. And that is extremely powerful. Persistent memory is more than just this nice way of booting quickly. Persistent memory allows a more efficient operating system and system environment because it eliminates checkpointing. In today's environment, a lot of applications, especially databases, do checkpointing. They don't want you to lose the fact that you deposited some money into your checking account. And so they checkpoint each database operation so that if power does fail, they can unroll back and restart from that failed operation. But that means that periodically, you have to stop your application and back it up to storage. And then run a while, and then back it up. And then run a while, and back it up. And then run a while. On average, in a data center, this is 7 to 8% of system performance, and therefore, 7 to 8% of system power that you're burning just to do the safety from power fail. Persistent memory allows you to eliminate that.
So what's the alternative if you don't checkpoint, then how do you make sure your data?
Oh, persistent memory. So that was what I was describing about the baby interface or RAM back DRAM, is that if your data is not lost if power fails, then you don't need to be doing this checkpointing at all, because you can always restore from that memory image because the memory image is not lost on power fail like DRAM does. Yeah, so this is implemented a couple of ways. Battery-backed RAM or persistent memory. MRAM, for example. MRAM is one of those memories that saves the data even if power fails. And so there are a number of ways to implement persistent memory. A lot of data center people don't really appreciate how important that is until they go through and they do this power analysis and see that they could save 8% of their system power simply by paying a little bit extra to get that energy source to back up their memories. You know, this actually raises a really important question. I'm glad you asked it, really, because it's total cost of ownership, TCO. TCO is not something that companies were very good at even 10 years ago, because they had procurement people who were paid and given their executive bonuses to buy the cheapest component, and system architects who didn't care about cost, who would say, yeah, go buy me persistent memory. And then the procurement guy would say, oh, persistent memory is 3 times the price of the DRAM, therefore we're not going to buy it. Ignoring the fact that over the lifespan of a server, that 8% power burn would have paid for that additional memory, that persistent memory, in like 6 months. Companies did not have architects that had responsibility both for purchasing and for system architecting to make those TCO decisions. And that's something that Google, Microsoft, Facebook, these companies have recognized actually only fairly recently. And then, like I said, that's why in the DDR6 discussions, those were the companies that stepped forward and said, we don't care about performance as much as power. You guys need to solve this power problem. Matrix math is, as you know, very heavily used in artificial intelligence. This is how a lot of the machine learning is done. It's how a lot of the inferencing is done. So these matrix operations are great in that things like Python is good at doing these, but there's also something that comes out of matrix math, and that is things like unnecessary parameters. If you're looking for a picture of a dog, why do you have their flight schedule as one of the parameters in that database? All it's doing is burning energy and not contributing anything to the final result. So don't just add arbitrary parameters because you think you might need them. That's one of the messages that comes out of that. Another is that a lot of the operations have one of 3 values: -1, 0, or +1. Decrement, stay the same, increment, as parameters in these arrays. This is a little crazy that we have so much of this class of data that is not really, again, contributing significantly. So a lot of improvements can be made by not having underutilized parameters, picking the appropriate data size for these parameters. Not everything has to be 64-bit floating point. And one of the low-hanging fruits that I'm personally working with some partners on is memory compression. If a lot of rows and columns are -1, 0, or +1, a whole lot of data compression can happen. And again, we can improve efficiency by getting more data more quickly, because it's easy to extract compressed data in the CPU once you've shoved it out over one of those power-hungry buses. Another one that's getting popular, and maybe Yost can address something like this, is that things like hardware multiply accumulate units are starting to become popular. A number of companies are looking at implementations to do the MAC in hardware so that it basically, the answer is coming out instantaneously instead of running code loops. Consider the temperature of your data. This is where that memory tier, that huge pyramid, becomes your guiding light. The pyramid says, make sure that your hottest data, the data that you access the most often, is very close to the CPU. Data that's not accessed quite as often, that can stay out in local memory, in 1 or 2 hop NUMAs. Data that's a little cooler can be pushed off into the CXL tiers. Data that's reasonably cold can stay in the solid state drive. And freezing data can just be out on the network somewhere. So these are considerations that we can all address both at the hardware and software level. The software guys pick which tier they're in, and it's incumbent on us hardware guys to give you the data so you can do this intelligently. I need to be able to tell you it is 285 clocks to get to my memory resource versus the 80 clocks of a DRAM access directly connected to the CPU, so that you guys can then calculate your access ratios and determine where to put data. So this is where hardware and software people can work together. So I still have a few minutes here. I'm going to give a quick taste about what it is that I do for a living over at Wally. So first one is that as I was doing this analysis for the Department of Energy and seeing that 20 kilobytes of data moving in and out of a rank of DRAMs, it dawned on me that, hey, maybe we could do things a whole lot more efficiently, first of all, by eliminating the DDR interface completely. The CXL protocol has everything that a memory controller needs. It has an address, it has a read or a write command, and it has data and metadata. Why do I need DDR? Why do I need HBM? I don't need any of these other memory interfaces, and I can drive the memory array directly off of that CXL packet called a FLIT. And so this split RAM, you make the width of the memory 1 FLIT wide. 64 bytes is 512 bits, plus you can throw in some ECC and metadata, and just have the whole word so that you can transfer 1 clock per FLIT. Now, it's not 100% efficient because it's still a destructive DRAM core, but at least it's 50% efficient. It's because I can do the activate and then the precharge to rewrite the contents back into the core. And so I'm at 50% efficiency versus 0.025. I've gotten a 2000x improvement in performance by doing this. And the subsequent power reduction of eliminating multiple power-hungry memory interfaces. Another thing I'm working on is storage, solid-state drives. Today, how does an NVMe drive work? Well, NVMe drive has flash on it, sits out on a PCI channel, often has a local DRAM where it will copy a cached version of a 4 kilobyte block. But then you're going to read it out through the CPU into the main memory. Then you're going to access it over main memory. If it's out on CXL, you're going to transfer it across CXL to the CPU to main memory. There's a lot of these power-hungry paths. And as I showed earlier, about 2.5% efficient. What I'm working on now is, what if I were to change that PCI protocol to a memory protocol? So I still use PCI to transfer data between the flash and the DRAM, but now I use the memory protocol to get only the 100 bytes that on average I need out of there. So now I've gotten to an efficiency of 78%, or 31 times better than today's SSD resources. So we're at the closing of this. Hardware matters. Think about what the hardware is doing when you write your software, and think about energy efficiency, because this is going to be huge for everybody. This is not just for this industry, but for the whole world. Architectures are changing. I recognize that. It's a reality that yesterday's AI algorithms are going to be obsolete 18 months from now. People are talking about moving to hyperdimensional vector analysis and moving away from CUDA. These kinds of changes, they're happening. We need to roll with them, but we need to be smart as these changes occur. It's not just a hardware problem. You guys are part of the problem, and therefore you're part of the solution as well. So choose the right language. Please, please, please get the industry working on better compilers. We need good compilers. And when you do your matrix math, make sure your matrices are optimized. Be aware of the memory tiers. Know where data should be in the hierarchy in order to optimize performance and power. And just leave data where it belongs. I think we will see an increase in the number of processing in memory solutions, but those are very tough because they don't work with today's APIs. So I wouldn't give hope that processing in memory is going to be the panacea that it sounds like. Not all APIs are the same. Choose the right API because they can be orders of magnitude difference in the effectiveness of you choosing like a DAX API over a file I/O API. Look at persistent memory. Ask your companies, can we move to the support of persistent memory, even though it's 3 times the cost of DRAM, because we will pay for it by saving power and improving performance over the long run. And I'm still working on the memory compression thing. So let's work together. Let's see what we can do. Before I step aside, though, I want to give a call out to my partner, Cecilia, and the Bridge to Connect organization. I know at least a couple of the students in here have come from the program or been involved with Bridge. But I'd encourage you guys to all look at this as well. Bridge is a nonprofit that does mentoring of university students in STEM fields and helps bring them up on the things that universities don't teach. What are career paths? Public speaking skills. Not only teamwork, but leadership. These are skills that we're going to need in this coming generation to tackle the big problems that are coming along. And we're working with the US government and hopefully seeking funding from the CHIPS Act to help pay for the re-education necessary in this ever-changing world. And at that point, I'd like to open it up to open discussion.
And it goes up.
Thank you, Bill. So I think what we're going to do, we have a microphone we're going to pass around. So if you have a question, raise your hand. But I think we'd like to get questions. We'd also like to get discussion. So if you have a thought on what you or what the industry, software industry can do to improve energy efficiency, share that with us, okay?
So my question is, very good presentation though, on hardware basically, but I had some thoughts and observations on the presentation. And the energy crisis is there for sure. I mean, I can see it coming. So my question is, and question and observation both. So what the architecture we are following is basically what we call it as a classical computer, I call it. Have we looked at alternate architecture like a quantum computer, which actually manages the information in a very different way? So the reason I said that all the classical computers are based on the invention which was done 50 years back, which is a transistor. And we have millions and millions of transistors. Like right now per person, there are like 40 million transistors in the earth. So this can be solved if we shift to an alternate architecture where instead of using a traditional resistor, we use a CT, like a single electron transistor, a different architecture. In a typical classical computer, you have 1 byte, and everything has to fit into that. But in a quantum, we have a qubit. So there, actually, you can put 8 qubits, and all qubits can operate independently. So that's another thought that, maybe an alternate architecture in future, might solve this problem.
Oh, yeah, to repeat the question. The question is looking ahead to quantum computing and what are the implications of that in terms of the context of what we're looking at. So I have a number of answers to that. First of which is I've spent, some tens or maybe low hundreds of hours studying quantum, which means I've taken a sip out of the ocean. So I don't know enough about the impact of quantum from the power perspective. But I do know that I'm also in charge of writing the specification for the next generation of system management buses for computers. I did that for the previous 4 generations, DDR1 through DDR5. So now in DDR6, what we're going to be doing is we've been told by the NIST to prepare for post-quantum. And so the impact is that with our DDR5 solutions, we were able to keep the security keys down to about a kilobyte per key. We've been told that in post-quantum, the algorithms are probably going to jump to 120 kilobytes per key, and we're screwed. Our chips are only 2 by 3 millimeters. And there's no way we're going to be able, and you can't have just one security key, because security, if you know the DMTF format, you basically need like 8 levels of keys. That you need one that is at the chip manufacturer level, one that is at the module manufacturer level, one at the system OEM level, and so forth up the chain. So 8 keys times 120 kilobytes, and these chips, these system management chips, are built on like 65 nanometer processes. 120 kilobytes times 8. We're talking about our chip sizes jumping maybe an order of magnitude, maybe from 6 square millimeters to 60 square millimeters. And yeah, it's a big problem, and I'm personally facing it every week. And I don't have an answer yet. Hopefully I can come back in about 3 years' time and give you what the answer is.
Thank you.
So I guess one of the things on the software side, it's been a while since I've coded myself, so maybe this is misplaced. I'm not sure, but it seems like with all the pressure to churn out, volumes of code and stuff going on everywhere, it strikes me that to get to the kind of place where you're talking about for software engineers to take responsibility, there's got to be better tools, right? Because it's sort of like, lint, solve like, syntactical stuff. You need tools that'll tell you, hey, there's, easier ways to spot latency problems. Because today, I tried to spot that there's a latency problem that could be resolved because, you could have done better use of, variables. No one's going to make that connection, right? I mean, the tests to even figure out latency are kind of complicated.
Yeah.
And based on your talk, I'm using latency because I notice you oftentimes equated latency with power usage. So that strikes me as potentially a approach to try to get to tooling that could help engineers. But personally, I just don't think it's going to be it doesn't seem like a very practical way to approach it, to say, hey, as software engineers, just be aware that there's all these options and you're going to pick the right one and we're going to trust you. That just doesn't strike me it's going to work well.
And there, to repeat the question, then the question was about can't put the burden completely on software people to deal with these energy optimizations. And there are a lot of answers to that. First of which is, of course, yes, we do need better compilers. But I will also point out something from my past in that for a while I was the memory specialist for Transmeta. And Transmeta had a really interesting CPU that took over the Japanese market at one point for notebook computers, executing the Intel x86 instruction set using a VLIW engine. And the approach was really interesting. What we did was we ran the Intel instruction set interpreted. But we had hardware monitors in the chip that noticed and detected loops. And we could set thresholds. If a particular piece of code got executed 10 times, you're in a loop. Invoke an optimizer. And we would pause, optimize the code, and then restart it. And then we would detect if it was executed 25,000 times. Invoke a second level optimizer. Detect that it was executed 500,000 times. Invoke the highest order optimizer. So this is a great example of hardware and software people working together to not put the entire burden on the software up front, but to let the hardware assist in figuring out when to optimize.
But what happened to us?
What happened is that TSMC fell on their face trying to produce 130 nanometer process technology, and we lost all our customers.
So if I could just take a couple comments here. So the question that was raised
Yeah.
is how would a software engineer be able to do these optimizations?
Yeah.
And software engineering is built upon this principle of abstraction. We build software on using layers and layers of abstraction. The guy who's building that piece of software doesn't know what's going on underneath. And back in the 80s, there was a discipline that I know was, UC Austin. I think it was the software performance engineering discipline, which probably didn't go very far, but the notion was that there was tooling and methodologies for software engineers to actually essentially get spec and build software to performance criteria. That could be energy as well.
Right.
So that type of stuff, I think, needs to come back addressing these things.
Yeah, I agree. And in particular, measurement tools. And I think that addresses your question, right? You guys familiar with Memverge? Memverge is the company that makes a real-time performance detection, and then it optimizes things like memory tiering based on your execution profiles. You guys should read up on Memverge. They've done phenomenal work. And it's kind of cool the way they do it. They basically have a timer that kicks off, and they check the state of the machine when the timer goes off to detect where you're spending time and where your resources are being allocated. It's really cool.
Yeah, there's been a lot of people called software profiling has been around for many years
Yeah.
and this kind of stuff.
Yeah.
The only thing I want to make is this sort of machine optimization. It sounds awfully similar to GIN compilation. So if you look at like Java and other interpreted languages that do compilation based on hotspots.
Yeah.
So I wanted to add to that comment and discussion and address this really opaque nature of the performance, the system performance. I remember myself, I was taught in information retrieval, compressed but not down below the byte level because you couldn't possibly do anything quicker with something that's less than a byte adventure. And I was able to perform my libraries bit level, and I, just blew my predecessors out of the water with that performance. So at one particular time, I had a really clever little quicksort algorithm on 10 bits. So because 10 bits, I can choose my sizes appropriately, fill the caches up, and do very, very fast quicksort. But I come back to the programming a few architecture years later, and this thing is now slower than it would be if it wasn't compressed. So there's just a lot of factors in that, as even if you can obtain superlative performance at any given crossroad, it's really not guaranteed that some hardware guy later is going to go spoil your
Yeah, to summarize the question, it's about evolving architectures and how a solution that is optimal at one point in time is not going to be optimal forever. And that is absolutely true of every coprocessor that I've ever seen. Even Intel tried to take the 960 and turn it into a coprocessor at one time, and it failed miserably because with the amount of attention for the development environment for the 960 RISC processor And the development environment for the x86 mainstream processor were orders of magnitude different maturity levels and investment levels. And within 18 months, the main CPU was outrunning the coprocessor. So that is a treadmill. And that kind of goes back to my skepticism that processing in memory is a panacea, in that maybe you implement a Mac in a memory today, and that seems like it's a great idea because you're able to do it 10 times faster than the CPU can do it. But all of the attention and architecture improvements is going to the CPU, not to the memory Mac. So again, is in 18 months, are you going to be the bottleneck instead of the accelerator? And I don't think there's an answer to that personally.
But during the presentation, you discussed, removing the DDR interface and actually adding the CXL. Now, my question, I'm trying to envision, then we actually we have two different semiconductor process for the DRAM and then, if for the interface itself, so are you looking at chiplets or what?
Yep.
What I see.
The question was, when I talk about the idea of eliminating the DDR interface and going directly from CXL to memory, it is a multi-chip solution where the base chip would probably be done in a 7-nanometer process for logic, and it would be bonded either through three-dimensional stacking or wire bond to a wide I/O DRAM done on a DRAM process. Chiplets are definitely a trend that is expanding in importance, and there's a phenomenal amount of work going on. There's a UCIe consortium that is working on that. Also, it was a big part of the Department of Energy report.
You mentioned at one point avoiding unnecessary data because it's just going to take up extra space and use more power. But the problem software people come into is if they don't provide for adding data later, they've created a bottleneck that the software will never keep up with. And I have a separate comment after you answer that question.
Well, okay, so
Separate comment is
to put it in the context of the analysis that I showed, it was specifically file systems doing database access, doing sort, doing fsync. Those applications are, a lot of the movement is in indexes. The indices are being sorted, things are being added to linked lists, and so the accesses are very fixed in size and have been for 20 years. So at least in the context of what I was showing, there's probably not that particular problem.
No, I'm not saying there's anything wrong with what you said. Just that the software people need to keep in mind that there has to be a plan for what to do when you have to add more data that you didn't plan for initially. And if you don't do that, then you start over. And if you start over, that's just not cost effective.
Yeah.
I would also point out that you're really discussing the same problem that we in California have with water. We're asked to conserve water because it's running out, but the alternative is to save more somehow, to get more water. Well, the alternative to your problem is getting more power.
Yeah.
So what is the chance of that?
Yeah, and I faced that in my own software development in the past as well. You think that you allocated a megabyte and then when you run out, it's like, oh crap. I don't know. Do you have a suggestion for how we could put that in this context?
That's what the software people need to do, is think ahead.
Think ahead.
Yeah, from a software perspective, it appears to me that a lot of what you touched on here is what happened in the early days of computing. If you only had 3K of memory to work with, you had to worry about what size your variables were. You had to worry about how to solve the problem. But what happened was the message was memory is cheap, processing is, just programmers are expensive, just go as abstract and as high level as you can.
I was
and
there.
that message has to change. Yeah, that message has to go to the universities that are teaching students.
Yeah.
Okay, because this, you know, as the memory gets more complicated, the architecture gets more. The software developers don't see any of that information.
Yeah, and so going back to the Department of Energy report, one of the things that Cecilia and our partner Tim and I contributed to the DOE report is the need for that outreach. We need to get awareness of this problem out there. I'm curious, how many people were aware that this energy crisis was on the horizon? Oh, okay, most people. Okay, so that's a good sign that the word is getting out that this is important. Yeah.
Yeah, the word is getting out that it's important, but nobody understands why it's important.
I think to Neil's point, maybe the other part of it is that the message isn't that you have given a job to write some software and giving up budget in terms of energy. You might be given some operational budgets, but if you're working for a startup, where you might want to do produce something novel that makes no economic sense in the short term, like maybe LLMs. And consume lots of energy.
They do.
And you get acquired, and evaluations are crazy.
And so then people come up with SLMs and find out that they don't come up with as good an answer as the LLM.
Well, maybe we should talk about LLMs a little bit, because for those of you who are interested, and I'll send out an email afterwards. There's an IEEE short paper on the subject of essentially large language models, AI, and energy efficiency. And it talks about some of the things that Bill talked about, more from a software perspective as well. So it talks about things like, trying to make smaller models, trying to, if you're going to have a large model, there's the techniques for starting a small model to kind of leverage it out to a larger model, reusing a model, so you don't have to create and train models as frequently, and such. So there's a whole bunch of these types of things. And we had a talk a while back by Bill Daly from NVIDIA. He's the chief science officer there. And he spoke about some of the topics that we're talking about here. For example, using different numeric representations. Don't go for big floating point representations. Go to some fixed point, small representations, different matrix, implementations, that kind of stuff. So all this stuff's happening. And just, things are happening faster in terms of the use of it.
I think I'd also like to turn that observation around the other way. That you now know that if Google and Microsoft and Amazon and Facebook are telling the memory guys to get more efficient and consume less power, that means there's a market for products that are more power efficient. So if you're a startup company and you're producing a product, there's your differentiator. Think about that differentiator and its ability, because people are now finally doing total cost of ownership analyses that they didn't do 10 years ago.
Yeah, so first of all, thank you for the fascinating talk, right? And I think it's probably closer to the hardware layer, right? People are more aware and have more action plan. But I think when you go up, I think as Dan pointed out, right, when you go up to the software application layer, this just feels so far away and they have very little control of. And so we're talking about some pretty tremendous behavior change, right? So, and I think the only ways to make such a behavior change, one is there's a financial incentive, or two, there's a regulation. You have to do it a certain way. So what's your point of view about what can be the incentive?
I think you just named it, right? Money or contract. So the question is, what can we do as an industry to drive these? And that's exactly the right answer, is that we're all in business to make money, but we have a social responsibility as well. We need to balance those, and taking power consideration into account, like to Daniel's point, it's that if it triples the cost of developing your software, you may not make that money back. But if it's something that you can breed into your development environment so that you're doing it more cost effectively, then if it's not 3 times, but it's 1.2 times or 1.1 times the cost of your standard models, then again, you've done something that's socially right and still makes business sense.
So I'll bring up two aspects real quick.
Sure.
You provided numerous models showing the amount of data wasted upon return to the originator of the inquiry.
Yeah.
And you asked where is this data going to go? Where can all this wasted data go? And you also mentioned access ratio. I'm going to pause on that. My other aspect is, right now there's an emerging sector in blockchain technology called DePIN, Decentralized Physical Infrastructure Network. It's basically a peer-to-peer network of nodes. Nodes, that's all it is. So what I'm bringing up to you is, could a possible solution of that returned amount of data being wasted, could that dissipate amongst a peer-to-peer network of nodes, as in kind of picking up the trash, so to speak, before it hits the originator of the inquiry?
Yeah, I know what you're asking, and I'm trying to think through how we would architect improvements on it, because that's really what we're here about, is how can we improve on that? And so my point about leaving data where it is when possible, in that context, I would have to think through how the blockchain nodes are communicating. But more importantly, what are they communicating, and how much of the traffic is essential and how much of the traffic is overhead fluff? And I don't have enough data to answer beyond that.
Thank you.
But I'd love to hear inputs from you guys that maybe you guys are more in tune with that. Does anybody else have an answer to, in particular with blockchain, how much of the data is used versus how much is just moved around?
In general, blockchain itself is terrible in terms of energy consumption. So inefficient, right? Compared with a centralized solution.
Yeah. And now one part of the answer that I could give for that as well is that as we look at all fabric traffic, I come from the early days of, I installed Intel's first Ethernets with the big fat coax cable, and you put repeaters on that. And what was a repeater? Everything that got transmitted on any computer was broadcast to all computers through a repeater. And over time, we got smarter about filters on the switches. That might be part of the answer, is reduction in broadcast versus directed traffic.
But I think this point has some merits.
Yeah.
You can also have private blockchain, which is pretty much is not all over the place. And if you can implement that within a server environment, a song, it might be able to do something. But I think as some merit,
Yeah.
but it's a good for that.
Yep. All right. Great. Thank you so much for having me.
Now, we have a few tokens of appreciation for you for taking the time to speak to us. We have a certificate of appreciation here,
Thank you.
and we have something that you can drink. Thank you, Bill.
Sometimes I feel like I own stock in Starbucks. Again, thank you so much for having me. Good night, everybody.